Okay, here we are. This is Unit 4. This is the first video over polar coordinates. You can see the objectives on this screen. Polar coordinates were developed by James Bernoulli, that's how you say that name, 1691, although they think probably Isaac Newton did. Didn't he do everything? Here are the objectives, and I'm going to follow those objectives pretty closely on this video. On we go. Remember the SOHCAHTOA and the Pythagorean theorem. Not going to spend much time on this, but these are things you should have remembered from geometry, and we're going to use them in terms of polar coordinates. Okay, to introduce polar coordinates, we're going to start with a circle. The circle will be centered at 0, 0 on the Cartesian coordinate plane, the rectangular plane. And you can see that the radius of this circle is r, and the direction from the x-axis is in theta. And then a point on the circle has rectangular coordinates of x, y, so over x and up y. So this particular point that we're talking about here has rectangular coordinates x, y, and they call these rectangular. There's another way to graph this point using angles, and these are polar coordinates. Polar, like the ice caps. Polar coordinates are the length of the radius of the circle, and the second coordinate is theta, or the angle from 0. And this is 0 radians or 0 degrees, but starting there. So in other words, it would be going r units in the theta direction. And that's what polar coordinates are about. And doesn't that sound a little bit like a vector? Because it's true, it has magnitude and direction. Here's your magnitude, here's your direction. So polar coordinates. All right, so let's talk about some of the things we know from a right triangle. We know that this is x, and we know that this is y, and this is a right triangle. So we could write down one relationship that x squared plus y squared is equal to r squared. So you'll notice that the rectangular coordinates have x and y, polar coordinates have r and theta. And if you look at this Pythagorean theorem, you have x squared y squared on one side, r squared on the other. Okay? Another relationship that they have here are the sine, cosine, and tangent relationships. So for instance, the tangent of theta is going to be y over x. And so that's something that we could use. It has theta in it, so we could use the x and the y to find theta. So we're going to put this in our toolkit. And a toolkit is going to be something that we're going to use for conversion, so we're just coming up with those right now. The other two, of course, are sine and cosine. So if I have sine theta is going to be y over r, or I could multiply, y is going to be r sine theta. And you can see that you have rectangular coordinate on this side, and polar r and theta on the right side. So I'm going to write that in here. I'm going to write it y equals r sine theta. I'm trying to keep rectangular on one side, polar on the other. And then, of course, the last one is cosine, and that's x over r. And so x is equal to r cosine theta. So x is equal to r cosine theta. Okay, that's our toolkit, and that's how we would introduce that. I wanted to show you the differences between the rectangular coordinate system and polar coordinate system. You'll notice that the rectangular coordinate system is more like this. And so you would go over x up y. So if I had a particular point, say right here, then I would go over x and up y to get to that point. So rectangular coordinates are going to be x, y. Polar coordinates, on the other hand, are theta. R theta. So if I had a point that was right here, this would be how long is r, where you could count 1, 2, 3, 4, 5, and it's in the pi over 3 direction. So that coordinate would be here. Over here, I would have 1, 2, 3, 4, 5. I just happen to pick that, 5, in the 4 pi over 3 direction. Okay, so another way to write this point that I have here in red, there I don't know if you can see it, this one right here, another way to write this point would be to go out 5 in the opposite direction. Okay, so if I started here and then went in the opposite direction. So in other words, if I had negative 5, 4 pi over 3, means I go in the 4 pi over 3 direction, but negative, remember what negative means, it doesn't mean that it's a negative direction, it just means that it is in the opposite direction. So these 2 points are going to be the same point. Now, another point, to mention this one that I've colored now in blue, is to go all the way around once, right? 2 pi plus pi over 3. So that would be 8 pi over 3, and I go out 5. So now this point and this point are the same place. I end up in the same place. Okay, so for instance, if I want to do this point right here, and instead of using radians, I'm using degrees, then this would be, if I'm doing r theta, it goes out 2 in the 90-degree direction. Now, I could also do this point, right? Go in the 270-degree, but not go to end up back here at this point, I would say negative 2. So negative would mean that I go in this direction, but I go the opposite way. So here are some different ways that you can do the coordinates. So here's an example of what you might have. You might have a polar coordinate that, notice I have written just a little differently here. All this time I've told you that it was r theta. That's in polar. But if you start with a rectangular coordinate, x and y, remember from our toolkit, x was our cosine theta, and what was y? Our sine theta. So you could substitute for the x and the y and turn it into another set or another way to write the polar coordinate. But here's the example that we're given, 2 and pi over 2. So you always do the second part first. You find pi over 2, that's here, pi over 2, and I want to go 2 in the positive direction, so I'm going out towards the angle, so 1, 2, and here I go. Okay, there's my point. It says graph the polar coordinate and give 2 other names for the point. Well, one way that you could do this is to use a coterminal angle. Well, find another angle that's coterminal with pi over 2. Well, to find a coterminal angle, remember that the easiest way to do it, because there's an infinite number of them, is to take your number and add 2 pi to it. Another way to do it would be to subtract 2 pi from it. So, okay, so that would be one possible way to get 2 other coordinates, right? If you just find 2 angles that are coterminal with the given angle, and then write the 2 in front of it, and you're good. So you would write a 2 in front of that, and a 2 in front of that one, and you've got it. That would be 5 halves, would it not? Yeah, 5 halves. 5 pi over 2. Another way to do it, which is a little trickier, is to go 180 degrees, or go pi, in the opposite direction. So my angle would not be pi over 2, it would be 3 pi over 2. Well, I don't want to end up at 3 pi over 2 positive 2. I want to go in the opposite direction, so I would say negative. So here we've given at least 3 other names for this one point, whether we go all the way around once and end up here and go out 2, or we go backwards. We go this way, right, and end up here and go out 2. This one, we went all the way to here, down to 3 pi over 2, and then went backwards to arrive at that same point. One more example. It says I want to graph the point 9 pi over 3. So first I have to find pi over 3. This is 0, right? This is pi over 2. So this probably is pi over 3. Looks like it's divided into thirds. And I want to go out 9. So I start at the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there we go, graphed. So I go pi over 3, and 9 in that direction. I need 3 other names for the point, right? So I need coterminal angles. So I do pi over 3 plus 2 pi, which is going to be 7 pi over 3. And then I'm going to do pi over 3 minus 2 pi, so that's going to be negative 5 pi over 3. Okay, so there's 2 of them. So I want to go in that direction. That'll be 9 and 9, and my 2 coterminal angles. There's 2. The other is the one opposite. So if I go this way, this angle is going to be 4 pi over 3, but I want to go in the opposite direction. So it'll be negative 9, 4 pi over 3. And I want you to notice that even on this one, you can find an infinite number of coterminal angles. So these are 3 points. So you would have 3 points, your neighbor might have 3 points, someone else in the classroom may have 3 different points, because there are an infinite number of points that are coterminal with that point. So I hope you understand this part on how to graph, and then also to be reminded of the coterminal angles. The final objective for this video is to convert from polar coordinates to rectangular or Cartesian coordinates. In other words, we're going to go from polar, r theta, to rectangular, which is x and y. Now, it'd be really helpful to have the toolkit. The toolkit was x squared plus y squared equals r squared. Tangent theta is equal to y over x. X is equal to r cosine theta, and y is equal to r sine theta. So there we go. So I have 4 and 150. 4 and 150, these are polar coordinates, so I have r and theta, and I need to convert it to x and y. So I'm going to do both of these. So x is going to be equal to r cosine theta, which is equal to 4 cosine of 150, and y is r sine theta, which is 4 sine of 150. The sine of 150 is in the second quadrant, where cosine is negative and sine is positive. So the cosine would be 4 square root of 3 over 2, and the sine of 30 degrees would be 1/2. So 4 times 1/2 is 2. So I would have 2 square root of 3 and 2. And I want you to use the values off the unit circle. Off the unit circle. So I want exact values, not a calculator. You can check it on your calculator, but I want exact values. Okay, if you were graphing this, 2 square root of 3 is about 3.4 and 2, so something like this. Over here, if I'm doing it, I would do 150 degrees, which is right here. This is 150, and I'd go up 4. 1, 2, 3, 4. Oh, and I did this one wrong because this should be negative, and that should be over here. So these 2 points should be in the same place, with whatever coordinate system you're using. All right, so I hope you took notes, and please bring any questions. Some of this is the very first time you've seen it, and we're bringing our unit circle out of mothballs, so bring questions to class, and I will answer them then.